For geometry, this is section 12.5, probability and the multiplication rule. We've already dealt with problems like this before, so I'm going to run through this fairly quickly. The multiplication rule, so we're going to be multiplying probabilities together today. You're going to use the multiplication rule when you have compound events, which consists of two or more events happening. So what you're doing is you're not just pulling one card out or selecting one person like we've been doing in the past. You are actually like flipping two coins or drawing two cards, or maybe you're flipping a coin and drawing a card. So you're doing two events at once, and that's what tells you that you need to multiply. When you're doing two events, you have to multiply the probabilities together. If it's only one event, you're usually going to be adding the probabilities, okay? So for compound events, there's two different things that could occur. They could be independent of one another. Independent means that one event does not affect the other event, okay? A lot of times you'll see this if we are replacing something. So with replacement, if I'm drawing a card and then I replace it and then I draw another card, both of them are going to be out of 52 cards, right? I'm not going to have less of a chance of drawing a card the second time than I did the first time because I replaced it. Dependent events, one event does affect the probability of the other. So this is where you get a lot of times without replacement, okay? So if it says without replacement, they're going to be dependent. If it says with replacement, they are independent. The front side of this sheet is all with replacement. Let me make my screen bigger here, sorry. The front side of this sheet is all with replacement. And then without replacement or dependent events are going to be on the other side. So in example 1, all they want us to do is identify whether A, B, and C is independent or dependent. That's all they want us to do. So part A, one coin lands heads up, and then the second coin lands tails up. We have to decide whether they're independent or dependent. So in the second coin flip, I did, in between the second and first coin flip, I did not shave a part of the coin off. I didn't alter the coin at all. I didn't do anything. I'm going to have the same chance of it landing heads up on the first coin flip as landing tails up in the second coin flip. So those are independent events, okay? I didn't alter my coin at all. I have just as much chance of it occurring in the first flip as it was in the second flip. So part B, one student's name is chosen from a jar and not replaced, okay? So the second time I draw a student's name out of the jar, I have one less card or one less name in there. So those are going to be dependent events. Whoever I chose on the first draw, or the first student's name, whoever was chosen, is going to affect who is chosen the second time. And then part C, both Wednesday's lottery numbers and Saturday's lottery numbers are 1, 2, 3, 4, 5. Okay, that is a huge coincidence because lottery numbers are altogether really hard to predict, and the fact that they're both coming up 1, 2, 3, 4, 5 is just amazing. But Saturday's lottery numbers have nothing to do with Wednesday's lottery numbers. Okay, they are independent events. All right. I had just as much chance of drawing a 1, 2, 3, 4, 5 in that order on Saturday as I did on Wednesday. I don't subtract one of the numbers out or anything like that. So those events are going to be independent. Example 2, on each turn of a board game, a player rolls a dot cube. This is just a number cube, 1, 2, 3, 4, 5, 6 sides, and spin a spinner. Here's what the spinner looks like. It looks like you can spin green, blue, or red, probably. On Dion's first turn, he rolls a 3 and spins, and the spinner lands on red. Are these events independent? Well, a dot cube has nothing to do with a spinner. I'm going to have a 1 in 3 chance of hitting one of these sections on the spinner, and I have a 1 in 6 chance of hitting whatever on a dot cube. They have nothing to do with each other, so they are independent. All right. Explain using probability. This is what we're going to get into actually calculating probability down here. But the chances of him rolling a 3 on a dot cube, there's only one side out of 6 that has a 3 on it. And the spinner landing on red, there's only one section of the spinner that's red out of 3. If I multiply those together, because we're multiplying, two probabilities together we multiply, 1 over 6 times 1 over 3 is 1 out of 18. So there's a 1 out of 18 chance that I'm going to hit a 3 and a red consecutively. All right. Two independent events. The probability of two independent events happening is just the probability of the first event times the probability of the second event, just like I did up here. Probability of the first on a dot cube, the probability of the second on a spinner. All right. Example 3 is talking about going to a concert. So Mary Saul and her friends are going to a concert. They put 3 blue and 5 yellow slips of paper into a bag. Get into the habit of doing this. 3 blue, 5 yellow. Now I don't have to read that sentence again, especially if they give me a long list, like 5 different colors. I'm going to want to list them off to the side over here. Okay. If a person draws a yellow slip, he or she will ride in a van to the concert. A blue slip means he or she rides in a car. So this is car, this is van. All right. Suppose Mary Saul draws a slip and she does not like the outcome. So she puts it back and draws again. What is the probability that on each draw her slip is blue? So we're just going to do this one at a time. Here is my first draw and here is my second draw. Don't try to do them both together yet. The first draw, I want to know what's the probability of it being blue. Okay, there are 3 blue slips out of a total of 8. Okay, there's 3 out of 8. Now, that's just with her first draw. She's going to draw again because she didn't like the outcome. But the key here is she puts it back. So how many total slips of paper do I have in the bowl again? I still have 8. If she didn't put it back, I would only have 7 slips of paper. But this time I have 8. Okay, and again, I want to know what's the chances of it being blue. There are still 3 blue slips of paper in there if I put it back. I'm going to multiply those together. 3 times 3 is 9. 8 times 8 is 64. So she has a 9 out of 64 chance of drawing 2 blue slips in a row if she puts it back. Okay? Just to give you a little hint, if she does not put it back, it would look like 3 over 8 times 2 over 7. Okay? Since I'm looking at both of them being blue, I want to know this one being blue and this one being blue. If I don't put the slip of paper back, I only have 7 slips of paper now instead of 8. And I'm assuming that the one that I did draw over here in the first draw was blue. So now I only have 2 blue. Okay? So that would look like, 6 over 56 or 3 over 28. Okay? That's how the probability would change if I don't replace. This guy right here is going to be dependent. Okay? This one here is independent. Okay? Dependent is what we're going to be talking about on the back side of this paper. So there's independent, there's dependent. Backside. Probability of two dependent events happening is the probability of the first one happening times, we're still multiplying, the probability of, this is called the probability of B given that A has already happened. So probability of B given A. All right, that looks kind of confusing, but it's really not. Let's go to an example. So example 4, Cynthia randomly draws 3 cards from a standard deck one at a time. Now she's drawing 3 cards, not just 2. So this time we'll probably have 3 fractions to multiply together. Okay, not just 2, 3 of them. She's drawing 3 cards from a standard deck one at a time without replacing. This tells you dependent. Dependent, all right? Find the probability that the cards are drawn in the given order. A diamond, all right? You kind of got to know your deck of cards here. I've got one sitting up on my desk. If you need to look at a deck of cards, don't sit and play with them. But if you need to look at a deck of cards, there are 52 total. The different categories of cards are, you can have diamonds, hearts, spades, which look kind of like, I don't know, I'm trying my hardest here, spades, or clubs. Club is like kind of like a three-leaf clover. So those are the different ones, and there are 13 of each one of those cards, okay? Now within those, they are numbered, so you can have an ace, or you can have a 2 through 10, so 2, 3, 4, 5, 6, 7, 8, 9, 10, or you can have a jack, a queen, or a king. That makes up your 13 cards. So an ace, you'll have 4 of them because you'll have 1 in each suit. A 2, you'll have 4 of them. A 3, you'll have 4 of them. You'll have 4 kings, and so on and so forth, all right? So I want to know diamonds, the probability of me getting a diamond. There's 52 cards to start with, so that's my first draw. 52 cards, and 13 of those are diamonds, all right? Now, I am not replacing. So the next time I draw, there's only 51 cards in there. I'm assuming that the card that I drew on my first one was indeed a diamond. So this guy was a diamond. Not another suit, he was a diamond. I'm assuming I'm getting what I want. The next time I want to draw a spade. A spade looks like this. It's, I don't know, it looks like a shovel, kind of. There are 13 of those, okay? 13 out of 51, and the last one is a diamond again, okay? Now there are only 50 cards because I didn't replace the first 2. But since I drew a diamond in the first draw here, there are only 12 diamonds left. So I'm going to go ahead and multiply these together, but before I do that, let's reduce if we can. 13 over 52 is 1/4, so I'm going to go ahead and do that. 13 over 51, what will that reduce? Let me see. You can get your calculator out and do this just as well. Of course it doesn't, that was silly. 12 and 50, though, will reduce to 6 and 25. 6 and 25 if I reduce both of them by 2. This 6 and this 4 can become 3 and 2. 3 and 51 is 17 and 1. Boy, I'm just making a mess of this now. I think that's probably all that I can do. Yep, that's all that I can do. 13 is a prime number. All right, so on the top I have 1 times 13 times 1. 1 times 13 times 1 is 13 over 2 times 17 times 25. 2 times 17 times 25 is 850. So I have a 13 out of 850 chance of drawing those 3 in that order if I do not replace. In case you were wondering, 13 divided by 850 is a 0.015 chance, which is a 1.5% chance. There you go. Not very likely that I'm going to have that happen. Okay. Last one, example 5. Use probability to analyze decisions. In a carnival game, 3 cards are marked with stars. 3 cards are marked with stars. 3 cards are marked with circles. Now I don't have to read that sentence again. I've got them all put over here. All 6 cards are placed face down, and the player turns over 2 cards one at a time. If the first card is a star and the second card is a circle, the player wins a prize. Alec decides to play the game only if he has at least 25% chance of winning. Should he play the game? Justify your answer using probability. Okay, so, hold on just a second. Okay, I just want to make sure I was getting that right. It would make more sense to me if you're drawing 2 of the same card, so I wanted to make sure I got that right. If the first card is a star and the second card is a circle, the player wins. Okay, so we want to get 1 of each instead of 2 of the same kind. All right, I want to make sure I typed that in right. Alec decides to play the game only if he has at least 25% chance of winning. Okay, so the first card has to be a star. So how many stars are there? There are 3 out of 6. The second card has to be a circle. If it's a circle, I win, but I am not replacing these. So I'm assuming that this one was indeed a star card, okay? So how many circle cards are there still left? There's still 3, but I have only 5 cards left, all right? So what I'm going to do is reduce those if I can. 3 over 6 is 1/2, and 1 times 3 is 3, and 2 times 5 is 10, and 3 out of 10 is a 30% chance of winning. So, is he going to play? Yep, he's got at least a 25% chance of winning. He's got a 30% chance, so he's probably going to play the game. Okay? So there's that. Look at each one of your events that are happening one at a time. So this is a star, this is a circle, and then you're going to multiply those probabilities together. There might be 3 of them that you have to multiply together, but just be careful when you're not replacing and all that good stuff. Okay? That's section, what was it, 12.5. There you go.